Assalamu alaikum. My name is Anna Malik and I'm going to present IE5 motors, its chemical composition and efficiency ratio. Firstly, IE5 motor means International Efficiency Motor Class 5. Class 5 represents the latest technology of the International Efficiency motors. Now, what is international efficiency? International efficiency is internationally basically a standard that states the energy efficiency of low voltage AC motor named as international efficiency. Their main purpose is to promote high energy efficiency to reduce the power consumption and energy cost of low voltage AC motors. AC means alternating current motors. Estimated 30 million efficiency motors purchased annually by the industry. There are currently around 300 million international efficiency motors which are being exploited. Altogether, international efficiency motor use an estimated 43 to 46% of global electricity demand with 60 to 70% of demand in industry. Given the importance of energy consumption by a efficiency motor, energy efficiency is very essential to reduce the economic cost of its exploitation, with the estimated electricity saving the potential of 13,360 terawatt power annually, which coincides the annual reduction of greenhouse gas emissions by 8,579 carbon dioxide equivalents until 2030. It means it is very environmental friendly, it is eco friendly. The United States Energy Policy Act of 1992 initiated the standardization of efficiency motors according to the efficiency classes. That was a significant milestone for raising the efficiency of efficiency motors. Since then, the classifications of the efficiency class has been improved, resulting in the homogenization of the International Electrotechnical Commission. According to this, efficiency motors are classified as IE1 means standard efficiency, IE2 means high efficiency, IE3 means premium efficiency, IE4 means super premium efficiency, and IE5 means ultra premium efficiency motors. So that's why IE5 lies in the ultra premium efficiency, the most latest technology of today. Now, there we will discuss the journal discussion and the comparative study of international efficiency motors. Like we will discuss the all the classes of the efficiency motors. IE1 motor fall into the international efficiency class 1. Class 1 means standard efficiency. Its efficiency is just standard. The output of this motor is 0.75 kilowatt to 355 kilowatt. Poles of international efficiency motor class 1 are 2, 4, 6, 8, 10, and 12. Means number of poles are these. So the speed range is from 500 500 revolution per minute to 3600 revolution per minute. The revolution per minute frequency of IE1 class drivers is 50 hertz or 60 hertz, which is very small. So that's why we consider it as standard. The aluminium frame size for IE1 engines or motors is 56 to 200. It is the size of the frame. The cast iron we use, the cast iron is the raw material of this frame, and the size now will be 80 to 400 if we use the aluminium frame. If we use the cast iron frame, in the if we use the aluminium frame size, then the size range will be 56 to 200, and if we use the cast iron frame, then the size would be 880 to 400. The temperature class of international efficiency 1 motor is class B. Now we will discuss general discussion and comparative study of international efficiency motors of all the classes from standard to ultra premium efficiency. Firstly, we will discuss international efficiency motor class 1, which lies in the standard efficiency. The output of this motor is 0.75 kilowatt to 355 kilowatt. Number of poles for these motors are 2, 4, 6, 8, 10, and 12. Speed range is 500 revolution per minute to 3600 revolution per minute. Revolution per minute frequency of international efficiency motor is 50 to 60 hertz. If we use the frame size of aluminium, if we use a frame of aluminium, then the frame size would be 56 to 200, and if we use the frame of cast iron, then the size would range from 80 to 400. The temperature class of international efficiency motor 1 class 1 is class B. It belongs to the class B. Class B means it is just the standard class. The cooling technology of international efficiency motor 1 is IC411. The insulation class is now its insulation class is F class, while the temperature class is class B. The motor duty type is S type. The protection technology used in IE1 motor is IP55, IP56, IP65 and IP66. S type means it is the standard efficiency type. Standard efficiency is basically the standard, it is basically the level we have set according to which we have classified the international efficiency motor. International efficiency motor class 2 fall into the IE2 class of the international efficiency standard. As we have already discussed, the output of IE2 motor is 0.75 kilowatt to 355 kilowatt. It is as same as the IE5 motors. The number of poles, but the number of poles here are less, just three number of poles, 2, 4 and 6, while in IE1 we have discussed about 2, 4, 6, 8, 10 and 12 even. The speed range of IE1 motor is from 1000 revolution per minute to 3600 revolution per minute. The revolution per minute frequency for IE2 driver is 50 Hz or 60 Hz. The aluminium frame size for IE2 engine is 80 to 160. Cast iron if we use, then the size would be 80 to 400. Temperature class of this motor is class B, as in the IE1 motors. Cooling technology of IE2 motor is IC411. The insulation class is F class. Motor duty type is also S type, as we have discussed that it is the high efficiency standard of this type, so that is why it is also S type. Protection technology used in IE2 motor is IP55, IP56, IP65 and IP66. International efficiency motor class 3 lies in the IE3 class of the standard efficiencies. Efficiency, the output of the IE3 motor is 0.75 to 355. Pole are 2, 4, 6 and 8. Now the one more pole than the IE2 motor but less than IE1. The speed range is from 750 revolution per minute to 3600 revolution per minute. The revolution per minute frequency for IE3 motor is 50 Hz or 60 Hz. The aluminum frame size for IE3 motor is 80 to 160 and cast iron frame size is 80 to 400. The temperature class for IE3 motor is B class. Cooling technology for IE3 motor is IC411 and IC416. It is having two types of cooling technologies, IC411 and IC416. The protection technology used in IT motor is IP55, IP56, IP65 and IP66. Insulation class is also class F. Duty type of motor is type S1, S2 and S3. It means it is having the standard efficiency, high efficiency and its own efficiency means premium efficiency. Now, IE4 engines or IE4 motors fall into the IE4 class of the International Efficiency Standard. The output is 2.2 kilowatt to 230 kilowatt. The pole of IE4 motors are 2, 4, 6 and 8. It is just like the IE3. The speed range of IE4 motors is 750 revolution per minute to 3600 revolution per minute. The revolution per minute frequency for IE4 motors is 50 Hz or 60 Hz. It is just like the IE1 motors. The aluminum frame size is 100 to 160. Cast iron frame size for IE1 is IE4 is 100 to 315. Temperature class of IE4 motor is class B. Cooling technology of IE4 motor is IC411 and IC416. It is just like the IE3 motors. Insulation class is also class F. All the efficiency motors belong to the F class. The motor duty type is S1 type, just in but the S But the IE3 motor having the duty type S1, S2, and S3, it is just having the S1 means it is just having the standard efficiency, but it is its own efficiency standard is super premium efficiency standard. The protection technology used in IE4 motor is our engine is IP55, IP56, and IP65. Now let us see that in general, depending upon their frequency, number of poles, power, electric motor must comply with the efficiency limits specified in International Efficiency Electrotechnical Commission classification. International efficiency. Now let us discuss in general that depending upon their frequency, number of poles and power, electric motors must comply with the efficiency limits specified in International Electrotechnical Commission classification. When new technologies are commercially available, new efficiency classes are also included in this standard. Limits for nominal efficiency. Nominal means normal efficiency classes are the standard efficiency classes specified in International Electrotechnical Commission for four pole efficiency motors in the power range of 0.12 to 800 kilowatt. The difference between the efficiency of IE1 means lower efficiency and IE5 is a higher efficiency, which increases when the rated power decreases. This is particularly true for efficiency motors with rated capacities less than 10 kilowatt. Moreover, for efficiency motor with rated capacities between 19 and 260 kilowatt, the difference between them is high and low efficiency just. One is of high efficiency and the other is of lower efficiency. That is between IE2 and IE3 with IE1 is approximately between 0.5 and 1.8%. These are the efficiency ratios, efficiency percentages of these motors. Raising the energy efficiency of efficiency motors during their operation needs to be improved in the power quality with the introduction of the control strategies. That is why we are really in need of replacing the other with the other. For example, we replace the IE1 with IE2 and IE2 is replaced with IE3 and IE3 is replaced with IE4 and now the IE4 is replaced with the IE5. So, raising the energy efficiency of efficiency motor during the operation needs to be improved in power quality with the introduction of control strategies that ensure load factors and rotational speed requirements with the maximum efficiency. Moreover, replacement of standard efficiency motors means SEM with high efficiency motors has been indicated. The replacement of SEMS means standard efficiency motors with high efficiency motor was carried out either by independent decision of the companies or to comply with regulatory mechanisms such as minimum energy efficiency performance standards. Efficiency performance standards are mandatory compliance regulations that set minimum efficiency limits for new efficiency motors. Minimum energy the introduction of minimum energy efficiency performance standard has increased the efficiency of efficiency motors available in many countries. However, the scope of minimum energy efficiency performance standard is limited to the introduction of minimum energy efficiency performance standard has increased the efficiency of efficiency motors available in countries. However, the scope of minimum energy efficiency performance standard is limited to the commercialization of new efficiency motors and it is applied in few countries just. Several studies have evaluated the feasibility of replacing standard efficiency motors with high efficiency motors, estimating that energy and cost savings and using the payback periods and investments in new high efficiency motors for economic evaluation. However, these studies are based on the criteria and analysis methods that differ from the real operating conditions of efficiency international standard in the industry. It considers the same load factor and operating hours for the efficiency motors in the facility, typically a full load, for example, load factor at 100% and more than 6,000 hours per year. The depreciation of standard efficiency motors to be replaced by high efficiency motor is excluded from the economic viability of the investment. The The Electrotechnical Commission of Efficiency Motor is estimated based on their nominal mechanical strength, and mechanical strength is estimated from the electrical parameters such as voltage and current, which introduces errors in the result. Some studies only consider the use of high efficiency motors to replace standard efficiency motors operating at low load factor. As we have discussed that the load factor can be of 100% even, while others consider only one class of high efficiency motor with efficiency excluding load factor from evaluation from the assessment. In general, the use of these considerations that are remote from the real operating conditions can identify the poor investment alternative as economically viable. They are suitable. Implementation of such substitutions may lead to the inefficiency and economic loss. Moreover, in industry, the operation of most efficient motor rarely involves measuring individual parameters such as voltage, current, electric power, which make it difficult to assess the operational efficiency. Thus, once a decision is made and implemented, and it's assessing the feasibility of replacing standard efficiency motors with high efficiency motors is crucial for raising the energy efficiency in the industry. Therefore, the study aims to evaluate and compare the main criteria used to evaluate the feasibility of replacing standard efficiency motors with the high efficiency motors. That is why now we will use the most efficient motors in the latest technology in this world of today. So the most latest technology of today's world is SynRM. It was invented earlier, it was discovered earlier, but the further technologies and the further amendments have been made in its machinery to make it more viable and more valuable and more good for the future use as well. Now let us study the SynRM. SynRM stands for synchronous reluctance motor, which is the very highly efficient alternative to the induction motors. Induction motors causes pollution. This SynRM is comparatively less causes less pollution and is eco-friendly. SynRM synchronous reluctance motor is highly efficient alternative to induction motors in recent years and also useful for the future world. CNRM is more modern derived solution with interesting advantages such as low rotor inertia, high power to weight ratio, good acceleration performance, flow alternating process, low international material cost and ease of fabrication, which is the basic use and which is a basic advantage of these motors. Now let us study that why syn RM synchronous reluctance motors are highly efficient and why we use it and why there is a need of them in the modern world. So, due to the exponential increase in the consumption of the energy and greenhouse gases, which are the major problem in the 21st century because it leads to the depletion of the energy resources and climate changes respectively, with 30% of the world's energy and 36% of the greenhouse gases generated by the electric motors used in the industry, we need highly efficient machines that reduce energy consumption and also decreases the carbon footprint and also decreases the carbon dioxide emissions and other harmful gases emission. So, manufacturing of Sinaram is very important. Among electric motors, asynchronous motors, which called as induction motors, were widely used in the industry because of their low cost and simple structure. However, induction motor efficiency is not satisfactory. It is not up to the mark. Besides low efficiency, these machines have other drawbacks. For example, difficulty in controlling speed, large power losses, heavy weight, and low torque capacity. Therefore, in recent years, building lighter electrical machines with high efficiency is the basic demand. These are also having the high torque capacities, so these are very important for today's. Given the shortcomings of induction motor, it is necessary to search for the alternative electrotechnical alternatives. In addition, with the development of the power electronics circuit design, driver control machines have also appeared. As an alternative to induction motors, permanent magnet synchronous machines were first designed and recently introduced into the industry, especially in electrical vehicles. Although these machines achieve fairly high efficiency but can be controlled by modern motors. The magnets used in PMSMS means permanent magnet synchronous machines are very expensive and their production depends on far eastern parts, especially China, leading limited access to them. The inefficiency of induction motors and very high cost of permanent magnet synchronous machines lead researchers to find another alternative to these machines. So the basic and the most technological and the cheapest and the advantageous technology is the synchronous frequency machines, in which under which class we take synchronous reluctance motors that are called as SynRM. It is because it doesn't contain magnets, it is more efficient and less expensive than permanent magnet synchronous machines. It is superior to induction motor because it has low energy losses. CNRM also has attractive properties such as better stability than induction motors with higher torque capacity and torque per size. The main reason for the high efficiency of synchronous reluctance motors compared to induction motor is the rotor, which doesn't contain conductive material. Rotor is the tool or the important equipment of these motors, which result in the lower rotor power losses. Power losses will be minimized. Since there is no CNRM coil in the rotor, the temperature of the rotor in these machines is much lower than the induction motor. So these machines are sometimes called cold rotor machines. In addition, synchronous reluctance motors have low temperature, result in the longer service of life, and longer service life means that it is also eco-friendly. CNRM also works in synchronization, which gives new riders sensorless control over these machines. Moreover, SynRM is cheaper and more accessible than PMSM, permanent magnet synchronous motors, due to the absence of permanent magnets in the rotors. On the other hand, the main drawback of SynRM in the past were its high torque ripple and low power factor. SynRM torque ripple is determined by using different rotor slot pitches for different barriers, asymmetric poles, skewing and determination of optimal width of ribs, asymmetric barriers, radial positioning of flux barriers, use of mixed layer windings to improve the power factor of SynRM, or coil dual layer configuration can be used. The formation of the flux barrier also improves the power factor of this type of the machine. In the study, a comprehensive analysis of TLA type CNRM is also performed. TLA type was discovered that was transversely laminated anisotropic CNRM. There was also axillary laminated anisotropic CNRM. But nowadays we are using TLA, means transversely laminated anisotropic type CNRM, and we will study the parameters on which it is working. We will study its working principle and how it works and why we use this latest technology in the new modern motors, because it is highly efficient, and we will also study the efficiency ratios in every part of these motors. is per- TLS types in RM is performed including rotor design, connectors for each slot, and influence on the wire size. These two parameters affect the stator slot occupancy and exceeding a certain percentage of these factors. These prevent the coil from being placed in the stator. These are the slots which are present in the machine are the motor values have the specified percentages, although analytically determined, or not experimentally feasible. Therefore, consideration of these parameters during scenario analysis yield more realistic results. In addition, current and voltage harmonics are also observed. Harmonics means frequencies. and variation in mechanical efficiency and power factor with load are calculated experimentally. The details on the basis of which analysis and test will be performed are given below. The parameters include rated power, rated voltage, rated speed, winding connection, pole number, number of stator slots, rated frequency, stator outer radius, stator inner radius, router outer radius, and router inner radius. These all are the parameters which are very necessary for the analysis that why this motor is highly efficient. Now we will study the initial design of these motor, how they process, how they proceed, and we will also study its finite element analysis which leads to its chemical composition. Now let us discuss the initial design process and finite elemental analysis of the SIN-RM. That why it is highly efficient. The initial design is based on the design of the rotor flux barrier, including the effect of the barrier numbers. Barrier numbers also influenced by the resistance, which is due to the flux of the barriers, and flux barriers is due to the rotor flux. Connector for each slot and corresponding wire sizes also matter. The angle of control means beta insulation angle, and the beta insulation angle comes in the ratios between the d axis and the q axis, and the width of the transverse and diagonal sides. As we are studying about the TLA types in RM means transversely laminated and isotropic in RM, so we will study the transverse sides of the rotor technology. During the analysis, the segment and the barrier width are determined by the ratio of the magnetic motive forces of the successive segments or the difference in the magnetic motive forces between these barriers. This study also assumes constant and equal flux barrier permeability and uniform flux density in all the sections. When the magnetic motive forces distribution rule is used to design the iron which we use in this motor technology is cast iron, which provide insulation in the rotor. The duration of the finite elemental analysis performed varies from 0 to 1 depending on how long the steady state performance parameters are reached. In addition, the time step used during the analysis is just 0.8 millisecond, which is a very short time. Now we will see how the flux barrier number influence the insulation or the resistance in the rotor barrier in the rotor technology. In the first analysis, the ratio of the iron to air on the q axis is taken. The dielectric constant is 0.5. However, the only consideration in the analysis is to know how the performance parameter of the device are affected by changes in the number of the flux barriers and to get the optimum flux number. So the initial analysis of air distribution is not taken into the account. It is not considerable. Further analysis of the new CNRM, a comparison was made on the effect of the number of flux barrier on the performance parameter of the machine, and the results are shown in the table. During the comparison, the position of the rotor stabilizes at about 52 degrees Celsius, which gives realistic results. Now, there are some parameters which influence the rotor technology efficiency. First is the barrier number. Barrier number may be 1, 2, 3, 4, and 5. Next is the output torque, torque ripple, output power, total loss, saliency ratio, power factor, and then we will get the efficiency percentage. The maximum output torque is obtained with the structure with two buffers in the same position. Buffers can be the barriers as well. However, the torque ripple of the design is much higher than the torque ripple of the 4 barrier and 5 barrier design. So, this design is not considered as an ideal design. Although the factors these factors psi and cos theta and value of the designs are worse than last three designs. The last of three these design has the lowest number of torque ripple and the lowest total energy loss. So it should be considered as the optimal design. To reduce torque ripple in the design, an optimization was used and detailed in the subsequent step of the investigation. So now we will study the effect of conductor per slot and wire size, how they influence the rotor technology. Fact, the wire diameter used for the coil about 140 newton meter torque is maintained during this analysis. This table shows the conductor variation per slot and the corresponding change of the mechanical performance parameter with the wire size. Now these parameters, which are conductor per slot, wire diameter, fill factor, rotor position, effective current, total loss, power factor, and efficiency. Now we can see that the conductor per slot ranges from 25 to 30. Wire diameter is decreasing as we are increasing the number of slots. The fill factor is also varying, and rotor position is also varying. Effective current is varying, total losses are varied, and power factor also varies, and efficiency ratio also varies. Now, the effect of beta controlling angle, which we also named as inclination angle of the rotor slot. It has the value of ASP, which can be obtained by placing the end point of the diaphragm on the D axis, as we can see in the figure. These angles can be specified at the fixed or variable intervals during SINRM construction, when we construct it, when we fabricate it. In this study, it is defined as a control parameter of the slope angle of the upper diagram, opening of the rotating diaphragm, which is very effective in the operation of the machine. By introducing this parameter, we can adjust the barrier endpoints to get better results, especially by reducing torque ripple torque. Moreover, the effect of beta controlling angle on output torque is less than that of the ripple torque. The figure shows that beta controlling angle is also the angle between the q-axis and the imaginary point. The table shows the effect of the parameter on the analyzed sin RM performance, that how its efficiency can also varies with the beta controlling angle. The beta controlling angle ranges from 7 to 14. We will get the output torque, and it is also varying, and it is also decreasing. Torque ripple percentage is also decreasing. Effective current is also decreasing. Losses are also decreasing. Saliency ratio is also decreasing. Power factor is also decreasing, and efficiency is also decreasing. If we control the beta angle, it means it is the controlling factor of the SIN-RM technology. From this table, we can see that cos theta and gamma generally tend to decrease as the angle increases. These all things are decreasing, as we can see from the table. Output torque and output torque and current. Usually, current output torque and IRMS usually decreases with the increment shown in the table. As we are increasing the angle, then all the things are decreasing. However, output torque does not change significantly. It is just having minor changes for the value above beta 9 controlling angle, because the goal of this analysis is to obtain the lowest ripple torque with the which is at the beta 11, and it is chosen as the ideal value. Now, how the insulation ratios will affect the CNRM? The we made changes in these ratios to make this technology more better for future use. That is why we are studying the following parameters: effect of insulation ratios, the effect of DQ, QD, and QQ. Axial separation ratios on the analyzed CNRM performance is examined after obtaining the lowest ripple torque with beta angle in the previous analysis. The isolation ratio primarily affects the output torque of synchronous reluctance motor and is commonly used to increase the torque during the synchronous reluctance motor design fabrication. Basically, these ratios can be defined as a ratio of the total amount of the air to the total amount of the iron on the corresponding axis, either Q or D axis. The effect of dielectric constant on engine performance was first analyzed between 0.65 and 0.75, and the results will be shown in the table. We can see that insulation ratio in Q axis, output torque, torque ripple percentage, effective current, total losses, saliency ratio, power factor, and efficiency ratios. Now we can see that the efficiency is increasing as we are increasing the insulation ratio by inserting the dielectric constant. Now this table is showing that increasing Q from 0.65 to 0.75 improves the machine output torque by 14.53%, so that now the efficiency of the motor technology can be improved. This is because increasing the ratio increases the mass of the air in the axis and decreases the inductance on the Q axis. However, changes in dielectric constant have almost no effect on ripple torque, differing by only 2.11% within the specified range. In addition, current increases as the rate is increasing. Also, cos theta and theta vary non-linearly but generally tend to increase with the increasing dielectric constant. However, the machine psi gradually increases with the increase machine efficiency gradually increases with the energy with the increase of the dielectric constant due to the decrease of the L insulation ratio of Q along Q axis. Considering this fact effects, dielectric constant with the value of 0.7 is chosen as the optimum insulation ratio for the Q axis. This is due to the low ripple torque and high value of efficiency cos theta, and the insulation ratio on d-axis is another parameter that affects the performance of SINRM, especially output torque. The ratio varied between 0.3 and 0.4 in 0.02 steps. During the analysis of the effect on motor performance, and the time would be very short. So that is why it also improves the efficiency of the motor. Now we will see how the rev effect affect the SINRM efficiency. Using SINRM at high speed can be difficult because flux barriers are fragile and can deform at these speeds. To make SINRM more durable, rib connecting parts are required. While designing the rotor of the machine, speed spoke rib saturation is carried out by Q psi Q axis flux rib width has a significant influence on output torque and must be considered in rotor design. This is because expanding the sides increases the radial rib width along q-axis and increases the insulation ratio along q-axis, decreases as output torque decreases. In addition, the introduction of the rib increases the ripple torque of the machine. Increasing the rib width leads to the decrease by increasing the insulation ratio along q-axis by inserting the dielectric constant, which can lead to the decrease in the cos theta of the machine. The table shows the performance parameter as the radial rib width changes. Radial rib width changes from 0.8 to 2 and the output torque is decreasing. Triple torque is varying, it is increasing. Effective current is decreasing and total losses also decreases. Saliency ratio is also decreasing. Power factor is also decreasing, but the efficiency is almost same. It means it is having the nominal effect or on the efficiency of the SIN-RM. The table shows that output torque generally decreases as the radials becomes wider. Increase in the power losses leads to increase in the insulation ratio along the q-axis due to the increase in the iron content. So increase in the power loss from 1 millimeter to 2 millimeter leads to 13.54% decrease in the output torque. Also, due to the broadening and the widening of the radial ribs, insulation ratio along q-axis decreases and efficiency also decreases. Along also, as the width of the radial rib increases, effective current changes or decreases. Moreover, the radial pin width also changes, causes the losses of the iron and the copper which we have used in the fabrication of the SINRM. Considering all these results, a design with a width of 1 millimeter appears to be the optimal design, which because this value gives the highest among those that provide the required output torque. Tangential ribs near the air gap connect rotor parts like radial ribs. The use of tangential ribs near the air gap connect rotor part like radial ribs. The use of transverse ribs provides manufacturing advantages. The biggest advantage of the tangential ribs changes in these factors can lead to the efficiency of the motors. So the use of transverse sides increases the periodic component of Q along the Q axis. Moreover, these strips cause a decrease in the insulation ratio of along D axis that arise indirectly from the crosstalk of the Q axis on the D axis. Due to the decrease in the insulation ratio along the D axis and improvement in the insulation ratio of the Q axis, the output torque of generated fabricated synchronous reluctance motor generally decreases as the radial ribbons gets wider, and increase in the power loss leads to the increase in insulation ratio along the Q axis due to increase in the output torque. The use of the transfer size increases the periodic component of Q. This causes a decrease in insulation ratio that arises indirectly from crosstalk of the Q axis on D axis due to the decrease in insulation ratio, and improvement in the insulation ratio along the Q axis leads to the decrease in the insulation ratio along the D axis. So the output torque of the generated in RM decreases with the increasing tangential rib width. HT is shown in the figure. HT is a tangential rib width which ranges from 0.8 to 1.6. Now there are other parameters: output torque, ripple torque, effective crane, total loss, saliency ratio, and power factor and efficiency. As the tangential rib width increases, output torque is getting decreased. Torque ripple is also decreasing. Effective current is also decreasing. Total losses is also decreasing. Saliency ratio is also decreasing. Power factor is also decreasing, and efficiency is also decreasing. So it means that tangential dip width increase leads to decrease in the efficiency. So we should take the tangential dip width at the minimal. The table shows that when tangential dip width increases by 0.8 millimeter, efficiency cos theta and theta decrease by 11.96, 7.61, and 0.4% respectively. However, ripple torque is largely unaffected by changes in tangential ripple. Also, also we will see how fine tuning is the important parameter or the important technique in determining the efficiency of the synchronous reluctance motors. The preliminary design results are very satisfactory for output torque and the ripple torque. However, the cos theta of the device is lower than the previous one. Therefore, another optimization technique called fine tuning was come under consideration. Considering the d-axis and q-axis flux lines of the rigid rotor, especially the d-axis is mainly used to improve the cos theta of the new designs of the CNRM. Further tuning is intended to achieve the slight improvement in the efficiency. Achieving the maximum anisotropy is a major concern in CNRM design, because in the previous history, in the last years, we were using axially laminated anisotropic in RM. Now we are using transversely laminated anisotropic. So it is the basic concern of today's technology. Achieving maximum anisotropy is a major concern. So the key to achieving an anisotropic structure is to ensure a smooth path for psi D and reduce psi Q as much as possible. The condition result in high LD and low LQ. Mean insulation ratio for D should be high and for Q should be low, required in the CNRM design. This is because obtaining these inductances leads to high values of efficiency, cos theta, and output torque. In addition, psi D should be the free path to reduce D axis drag and increase Q axis drag. On the other hand, it should simultaneously inhibit psi Q at maximum level and decreases psi D at higher at low level. The magnetic flux line in CNRM rigid motor are also shown in the figure. Now we will see how magnetic field can be affected. The d-axis line is perpendicular to the q-axis line is shown in the right side of the figure, therefore creating the barrier geometry parallel to the d-axis. Flux barrier can be considered as ideal approach while designing CNRM. This is because creating this type of barrier simultaneously block psi q due to orthogonality. Orthogonality means q-axis may be become parallel along the d-axis, so it may cause overlapping. A barrier in the form of d-axis flux can be generated using the Ne-Joksky equation, which is called the airfoil potential function, and it is used during the fine-tuning process, and it increases the efficiency of the scenario. An exact copy of the new synchronization and new magnetic field intensity B is shown in figure. The analysis was carried out considering just one half of the machine, and we can see that figure B shows that the radial and tangential ribs have high B. High B means high magnetic field intensity, while the rest of the rotor and stator have low magnetic field intensity. It should also be pointed out that this change in intensity depends on the position of the rotor. A double layer winding scheme is used to improve the performance of the new CNRM which has been fabricated. However, the winding still use the delta connection. The fine-tuned CNRM was run to the length of 1 second in step of zero point 0.8 millisecond. Dirichlet boundary conditions were also used during the fine-tuning. In this case, zero vector voltage is assigned to the limit of the mechanical parts. That is why Dirichlet boundary has been used and considered. In addition, operating temperature and rotor position of the machine are set to 75 degree and 53.95 degree respectively. Difference in output torque and energy losses and tangential rib width and P copper and P iron in the process of fine tuning are shown in the figure. P copper and P iron are the power losses of the copper and the iron, because these are the materials, these are the elements which have been used in the fabrication of CNRM. Figure shows that the current of the machine stator is very high at startup, and both the output torque and copper loss depend on this current. So both output torque and power loss of copper reach about 9 times the steady state values displayed. The average output torque and ripple torque values obtained from each of the zero point 0.8 second and 1 second time interval of the fine-tuned CNRM are 140.8 Newton meter and 13.72 percentage efficiency respectively, and are shown in the figures as we have studied. Moreover, power losses of the copper and the iron may vary because of the variation of the micro machine within the specified range. As in the figure, the average value of power factor of iron and copper are 300.6 volt and 445.4 watt. These are the power losses and the power factor, and the power factor total obtained by adding both is 1131 watt and 385 watt obtained from the current analysis. Moreover, CNRM efficiency and cos theta were obtained with the accuracy of 9.0599 and 0.774. Table presents comparison between the originally designed CNRM and fine-tuned CNRM. There are the performance parameters: output torque, ripple torque, saliency ratio, efficiency percentage, total loss, and power factor. And we have seen initial design compared with the fine-tuned design. We can see that the fine-tuned CNRM is having efficient mechanism, and its efficiency is far better than the initial design which we have been using since years. Now it has been fabricated and designed on modern technologies with the greater efficiency. Now how the efficiency is being varied with the different loads, how the loads affect the efficiency. So, electrical machine cannot operate permanently at the same full load in the environment in which it is used. It is desirable that the efficiency should be as high as possible at different load values. So, we tested its SynRM in SynRM as it was made under various loads to see how efficient the new SynRM is under these. The results are shown in the figure in the graph. The figure shows that generated SynRM has efficiency of 95.2% at full load. The machine reaches its highest value, which is 95.3 at 75% load value. The efficiency of machine at 25% and 125% load is 94.4% and 94.6% respectively. Now the table summarizes the test result for manufactured SIN RM, which has been emphasized again that the machine test took 12,000 seconds and the table values were obtained at 11,757.8 seconds. Now these parameters are rated voltage, rated current, rated speed, temperature, output torque, ripple torque, input power, output power, total loss, voltage harmonics, current harmonics, power factor and efficiency. These all are determined for the fabrication of the SynRM. SynRM manufactured efficiency is 95.2, which falls within the IE5 efficiency class, which is the super premium efficiency class, subject to test tolerances under applicable International Electrotechnical Commission Act standards. Furthermore, the power factor achieved for the machine is very satisfactory, for example 0.784. Moreover, the harmonics of the line voltage and phase currents are very low, less than 5%. It must be stated that the instrument didn't make any vibration or noises during the test. It is also eco-friendly, also since the output torque of the motor is set to about 140 Newton meter. The resulting ripple torque is 1.5%. Moreover, the maximum temperature reached by the machine is 48.1 degrees Celsius and the current consumption of the machine is 42.7 ampere. As a result, manufactured Sinaram at the rated power has quite impressive results of the performance parameters and it is of high efficiency 95.2% and it lies under the IE5 efficiency class with 0.784 cos theta and 1.5% ripple torque. So it is the highly efficient IE5 motor. That is why we have chosen it in the modern technology of today's world. Now we may conclude from the whole study of the latest technology of efficiency motors and the highly efficient Sin RM, we can compare with the previous studies on Sin RM. The new Sin RM is more efficient than the Sin RM created in with efficiency of around 90 and 85% respectively in the past, whereas for the novel design is 95.2% placed in IE5 efficiency class considering the experimental tolerances defined by International Electrotechnical Commission. Moreover, the proposed design has 1.64 and 13.623 higher value of efficiency and power factor comparing with the past. To sum up, the proposed NRM has quite fascinating results with its high efficiency, power factor, and low torque ripple values. IE5 Sinara motor offers up to 40% lower energy losses compared to IE3 motors, as well as significantly lower energy consumption and CO2 emissions. So they are also eco-friendly. Now it's all done about the synchronous reluctance motor, which are the highly efficient motors of today's world. And thank you so much.